Okay, welcome to a lecture. Today we are going to discuss the summary of series compensation. So just similar to the summary lecture of shunt compensation. So this is the summary lecture of series compensation. Now, FACT devices, why we are using the FACT devices is only to enhance the power handling capacity of transmission line, existing transmission line, to improve the transient stability, voltage stability, and reduce the oscillations, means damping in the power system. So our objective is to modify the electrical characteristic of existing transmission line in such a way that the same transmission line can transmit large amount of power without changing much more changing in the physical changing in the transmission line, only connecting the shunt compensation or series compensation in the transmission line. So to modify the electrical characteristic, we are using some different type of FACT devices. So today we are going to discuss the series FACT devices or series compensation. We know that the limitation of power handling capacity of transmission line is governed by mainly two factors. One is the transient stability or steady state stability. Simply it is a stability, and thermal rating. So thermal rating, if you just if you discuss the transient stability or steady state stability, it is going to enhance with the help of bundled conductor, or it may be use of the shunt compensation and series compensation. So the first we will discuss the concept of series compensation. Concept of series compensation. And now this compensation is concept of series compensation is utilized to enhance the power handling capacity. That's we have discussed that if suppose this is the 400 kV transmission line, it may be say 765 kV transmission line, and if the length of the transmission line is the system voltage, it is in kV, and the length of the transmission line, say it is a 200 kilometer, it is a 400 kilometers or 600 kilometers, the power handling capacity of the transmission line increases in this direction with increase in the system voltage, whereas the power handling capacity of the transmission line decreases with increase in the length of the transmission line. And why it is? Because it is a decrease in the direction of length of the kilometer. Say it is the length of the transmission line, it is in kilometer. This is 200 kilometers, 300 kilometers, 400 kilometers, and 600 kilometers, isn't it? Now it is because of that the power handling capacity of the transmission line P is equal to, it is given that suppose the sending end voltage and receiving voltage, we consider the magnitude is same. So V square upon X, Rex is the reactance of the transmission line into sine delta. As the length of the transmission line increases, the reactance, total reactance of the transmission line increases, and because of this one, the power handling capacity of the transmission line start decreasing with increase in the length of the transmission line. And we know that the power generating station is far away from the load center, and we have to transmit the power from a long distance, and because of this long distance, the power handling capacity get decreases. And to improve the power handling capacity with the help of FACT devices is nothing but with the help of some power electronic devices, or by connecting device in the shunt, or by connecting some device in the series or combination of both, is nothing but the concept of FACT, is a flexible AC transmission system. Now our discussion is to concept of the series compensation. Concept of the series compensation. We know that the transmission line is represented by the two machine system. Let we will consider our restrict on the two machine system for better understanding. So this is the two machine system, where one end is the sending end and second is the receiving end. This is say sending end voltage Vs, receiving end voltage is Vr, the reactance of the transmission line is X, and current flowing in this is say I. So this is the Vs, this is Vr, and this reactance is X. And if you consider that the magnitude Vs is equal to Vr is equal to say V, the power P is equal to is V square upon X into sine delta. So this is the uncompensated line. This is the uncompensated line. This is uncompensated line, and the diagram for uncompensated line, that is P delta curve, we can draw. This is angle delta, and this is power P in this direction. Say this is the 90 degree. So this is pi by 2. This is 0 and this is pi. So the maximum power is say P maximum here, P maximum, and at some particular point the system is operating. So this is the operating angle delta, and it is supplying the power P, which is equal to this power P is equal to, we can write is V square upon X, or it may be P maximum sine delta at any value. So this is the angle delta at which the system is operating. We can operate our system higher value so that it can transmit large amount of power, but we have to keep some margin in the, it may be the application of fault, it may be the sudden increase in load, sudden decrease in load, and whenever there is a sudden perturbations are there, sudden application of faults are there, the system is going to oscillate, and there's a large chances to come out from the synchronism or from the unstable. So this part is a stable one, and whereas this part is a unstable region. So our point of interest is that our system should operate here in this direction only, that is the stable region, and we will operate our system much more below than the calculated value, and that is called as a conservative criteria in the stability point of view. Okay, now we want to apply the series compensation. So under such series compensation, we will connect a capacitor in series with the transmission line. So the same transmission line is there, only we are connecting the capacitor, and the total transmission line is divided into the two parts. For proper derivations or to draw the vector diagram under this one. So this is the rest of the diagram is as it is, means sending end voltage Vs. So this is Vs, sending end voltage, receiving end voltage Vr. Here we are not going to consider the what would be the way to calculate the values, that is derivations over there. Just we want to take the review or summary of series compensation. So this is Xc, total capacitor is connected Xc, but half of the capacitor is here and half of the capacitor is in this direction, isn't it? So under such condition, this is the voltage Vs, then it is a voltage Vr. Okay. This is Vs, this is voltage Vr, and because of this capacitor is connected, this is the minus J I Xc upon 2, and this is the voltage minus J I Xc upon 2, and therefore the total voltage is the voltage Vx. Okay, and here is the voltage Vm, center voltage Vm, that will increase the current, and because of increase in the current, the power handling capacity of the transmission line or the power angle is going to increase. So here the total value of the capacitor power can be written as P is equal to V square, as the voltage, magnitude of voltage Vs and Vr is same, we have considered. So it is equal to X minus Xc into sine delta, where X is the reactance of the transmission line and Xc is the reactance of capacitor which is connected in series, and it may be written as P is equal to it is equal to V square, as usual. It is V square divided by 1 minus K into X into reactance X into sine delta, where K is equal to Xc upon X, and it is known as degree of compensation. So if you want to increase the degree of compensation, the value of Xc is start increasing. So definitely it is going to happen. So where X effective, or we can write X effective, will be the X minus Xc, or it is equal to 1 minus K into X. This is we have written on the denominator. So this is our equation for further discussion, or it is our interest to discuss the equation P is equal to. Now this diagram is for the uncompensated line, but for the compensated line, this angle is delta and power is P. Say this is the pi by 2 and this is, okay, we'll enlarge some diagram. So it is pi by 2 and this is pi. So select, this is the equation, this is the curve without any series compensation. Without any series compensation, where no compensation means K is equal to 0. So this K is equal to 0 and we get the equation is same one. But whereas if you increase the value of K, the compensation is start increasing. The compensation, the power handling, the P delta curve will be like that. So this is, say, this is the curve when K is equal to some value. Again, we can increase. So K is equal to some higher degree of compensation. Higher degree of compensation. This is the equation. This is the curve. Say this is P is equal to, this diagram P is equal to V square upon 1 minus K into X into sine delta, where K is equal to, let K is equal to 0.4 and say this K is equal to 0.2. So if you increase the degree of compensation, the degree of compensation K is equal to Xc upon C. If the reactance value or the capacitor value is more, the degree of compensation is start increasing and the power handling capacity of the transmission line get increases. So this is the increase in power handling capacity at different angle. Now, if the angle, same operating angle, the power handling capacity also increases, and which is going to increase much more in the next discussion. So this is angle 0. Now we will proceed our same discussion with the help of this concept of the series compensation. Now we can improve the voltage stability. Voltage stability by series compensation. Series compensation. So definitely similar to the shunt compensation, we have seen the radial transmission line or radial system is there. Again, we will consider the same radial line or transmission system. So this is the sending end power or sending end end. It is connected with the variable capacitor or some capacitor. The value of capacitor or value of voltage across capacitor is going to change by some different method. We will discuss later on. Now it is the reactance of the transmission line, and now here this is the load is connected. The load is connected at the end of the transmission line, so it becomes a radial transmission line system. The voltage across load, so load, and it is equal to VL, and this is voltage is equal to VS, sending end voltage, and the current is. So from this one, it is found that the voltage stability or the relation between voltage and power, this is the power P, that is a percentage power, or it is in PU. And similarly, the voltage, it is also in PU. It is also in PU, and it says that the voltage is decreases without any compensation. So this is when K is equal to 0. But as if you increase the series compensation by increasing the value of K, the voltage will remain constant, and the power handling, the max PU power PU also get increases. Say this value is equal to K is equal to say 0.2, K is equal to 0.2, this K is equal to 0.4, and so on. So the second point is that by series compensation, it is possible to enhance the voltage stability or to maintain the voltage across load with the help of series compensation. The third point, we are going somewhat fast because it is a summary lecture. So improvement in transient stability. Okay, so the transient stability is the stability which pertains to the sudden and large disturbance which occur in the transmission line or in the power system. So first we will draw the without compensation, and next we will draw the with compensation. So say this is the P delta curve without compensation. So this is pi by 2, and this is the pi. So it is the maximum power which can be transmitted with the help of without any compensation, means K is equal to 0. This is angle delta, and this is power P. So as the system is operating where the mechanical input is equal to the electrical output, or system is stable at the angle delta 0, at delta 0. Now let the fault occur into the system. Say this is the system is like that. This is the prime mover. It is mechanically coupled with the alternator. And here it is connected with the infinite bus through reactance of the say system, reactance of the system is that, and it is the terminal voltage or infinite bus. The mechanical input is PM and electrical output is PE, is the electrical output. When the fault occurs on the transmission line, the power goes to the zero value. The electrical power goes to the zero value, whereas the mechanical power remain as it is. Means during the transient condition, the mechanical input will remain same. And when the mechanical input remains same, definitely the speed of generator get increases. That is, the speed of generator is greater than the synchronous speed, and hence the angle delta, which is greater than the its operating angle delta, isn't it? So delta is going to increase with delta 0, or it may swing with a large value. So during the when the power is equal to 0, power goes to the 0 value. Power here, the power goes to the 0 value, whereas the mechanical input will be there, and because of this mechanical input, the generator will accelerate, and at some particular time the circuit breaker opens and it regain, or it maintain again in the operating position. So because of this one, the acceleration area is going to increase, or it is represented by the acceleration area. So this region, this area is the acceleration area, or energy during this acceleration, isn't it? And as it is not going to come with the equilibrium, it will oscillate. So let the oscillation is up to this value, and again when the area A1 and the area A2 become equal, the system become stable. So this is area A2. So when area A1 is equal to area A2, the system will be stable. So this is the margin for the stability. This is the margin area. Let the fault cleared somewhat late, means the circuit breakers are somewhat slower and the circuit breakers open here. So it is the maximum angle at which the generator or the system will regain. So this is the angle, and this area means this area is the marginal area, or it is the margin of stability. It is the margin of stability. Otherwise, the system will be unstable. Now we will take the same P delta curve with some degree of compensation. So same diagram. Angle delta, this power is P, and this is the pi by 2. This is pi. This is the uncompensated line. This is one. This is pi by 2. Therefore, this is the pi, and this is uncompensated line. Now, but if you increase the K, that is the series compensation, degree of compensation, this would be the new P delta curve. This is the new curve. Now, the same fault is going to occur in the system. System is operating over here. Earlier, it is operating at this point. So this is the acceleration area. Up to this one, there is the acceleration area, and this is the deceleration area. Now here the deceleration area is up to this one. So here you will get deceleration area A2. So this is the area A1. as earlier because of the fault, where mechanical input is equal to the electrical output. At this time, this is delta 0, this is delta 1, this is say delta 2, and this is the deceleration area. So here we found that the marginal area, this marginal area is very large. So this is the marginal area. So we'll show by the shaded line. So this is the marginal area. Margin A dash, or this is the marginal area. So it is quite clear that if you use the series compensation, with the help of series compensation, definitely the deceleration area is large and we have large marginal stability. So it is a region or by which we can increase the stability region. So this is the second say application or the advantage of a series compensation. Similarly, one may increase one may avoid the unwanted oscillation, or it can be as says as subsynchronous oscillation damping. It is a subsynchronous oscillation damping, and it is damping is due to when acceleration or there is some change in mechanical input and electrical output. We know that it is a swing equation. The swing equation, just remember it. It is a m d square delta upon dt square is equal to pa, where pa is the acceleration power, or it may be written as m d square delta upon dt square is equal to pm minus pe. So when there is a acceleration, definitely acceleration, when the acceleration is there, when dp upon d delta is greater than 0, definitely there is a system is going to oscillate. And this oscillation, if the oscillation is more, the system may come out from the synchronism. And because of the modern power system, there is a large power system is there, so large moment of inertia is there, and the dynamic stability somewhat take more time, or it take more time to settle to the new value. So this can be avoided, or the damping can be obtained, or we can damp out the unwanted oscillation with the help of series compensation. So this is the say concept of the series compensation, as well as the advantage of series compensation. Now our objective is to know what are the different methods available to control the compensation. So the topic is become, give the name of topic as approach or approaches to controllable series compensation. So basically there are two ways. One is called as a variable impedance. First method is called as a variable impedance type control, and second is called as a switching converter type. Switching converter type series compensation. compensation. The variable type impedance is nothing but which we have discussed in the concept of the series compensation. We are going to obtain the X equivalent or X effective, which is equal to X minus XC. Means we are going to insert some capacitor value or in series with the transmission line in such a way that the portion of reactance is going to cancel out with the help of capacitor, and it is also called as a line length compensation. Virtually the line length of the transmission line get decreases, and just we have discussed in the very early point, if the length of the transmission line is small, the power handling capacity of the transmission line will be higher one, and as the length of the transmission line increases, the power handling capacity also get decreases. Now, in variable impedance type series compensation, there are some other methods. Means there are some methods are there. One is called as a GCSC. GCSC. It is a gate turn off thyristor control series compensation or series capacitor is there. Second is the thyristor switch series capacitor, and third is thyristor control series capacitor. Whereas in the series compensation, in the switching type, it is called as a static synchronous series capacitor or compensation. So it is called as a SSSC. It is not a capacitor, it is a compensation. Okay. So in the switching converter type, there is a static synchronous series capacitor compensation, that is SSSC. It is similar to the StatCom, whereas there are different methods are available to control the impedance of the transmission, impedance of the capacitive reactance or the voltage across capacitive reactance. Now we'll discuss first point is the gate GTO, that is a gate turn off thyristor control. Thyristor controlled series capacitor, that is GCSC. Our objective is to control the voltage across capacitor. I'm not going to discuss much more inside because it is just a summary lecture. So this is one thyristor, sorry, GTO, and it is anti-parallel connected. GTOs are there. And it is in shunt with the capacitor, which is connected in series with the transmission line. So this is the capacitor, which is connected in series with the transmission. This is transmission line current. Because our basic one, this is the transmission line, and it is a controller, fact controller, which we have learned in the basic of fact devices. Okay, this is the line, and it is going to inject the voltage in the transmission line, which is in quadrature with the current, with the transmission line current. Say this is the transmission line current, and that injected voltage either by the capacitor, either by the switching converter type mechanism, the injected voltage or voltage which we are going to inject, it should be in phase quadrature with the transmission line current I. So this is the capacitor C and voltage across capacitor C, and our objective is to control the voltage across capacitor. Voltage across capacitor. Now, first we will discuss the waveform. Say this is the current waveform. This is the transmission line current I, and this is omega t, or time t is there. This is the crest value of current I is pi by 2. This is pi and twice pi. Okay. So the gate turn off device means when the switch is, say this is gate turn off G1 and this is G2. If one of the G1 or G2 is, say, in the positive half cycle or negative half cycle, say G1 or either G1 or G2 is conducting, the current is going to flow from the JTUs, and therefore the current in the capacitor becomes 0 and voltage is equal to 0. VC is equal to 0 when switch, say we call as a switch SW, the switch SW is closed. When the switch is closed, the voltage across capacitor is equal to 0, and voltage across capacitor VC is equal to VC maximum or its normal value when switch SW is open. When switch is open, the current is going to flow from the capacitor and voltage across capacitor is going to appear. So this turn off instead of turn on, and when the turn on, turn off, first we'll write the turn off. Turn off, it means that it is not conducting, the voltage across capacitor will be there and voltage across capacitor will be maximum. So here the voltage across capacitor is maximum under the turn off circuit, isn't it? So this is the voltage across capacitor VC, and when VC is equal to there, when turn off delay angle is equal to 0, isn't it? Now it is turn off with some delay. So with turn off delay angle, what would be the diagram or waveform is there? So VC is equal to 0. Now with turn off delay angle, say just by the second color, when turn off delay angle, say, is gamma, so here the turn off delay angle is equal to 0. Say just we'll write where gamma is equal to 0, but here say gamma is equal to 1, gamma is equal to gamma 1. So under such condition, this is the voltage across capacitor. So this is voltage across VC when gamma is equal to gamma, where gamma is turn off delay angle. So when the turn off delay angle is increases, the voltage across capacitor decreases, and this is called as a blocking angle. The angle during which the JTO is off by this one, it is a blocking angle gamma zeta is equal to, it is total is pi minus twice gamma. So this is the blocking angle. So it means that suppose if you draw the figure with different turn off delay angle, it is like that. So this is pi, this is 2 pi, and this is 3 pi. Okay, so here it is positive half cycle, negative half cycle, again positive and negative, and so on. So first is the, it is going to at crest of the current is the maximum value of current, because in the capacitor the current is lagging by 90 degree. So when the current is equal to maximum, voltage is 0, so it is current is leading by 90 degree. So here say this is the voltage VC, voltage across capacitor VC is equal to when gamma is equal to 0. But by turn of delay angle, this is the new value of voltage across capacitor VC, voltage across capacitor VC, when gamma is equal to gamma 1. So this is the angle. This is the angle. It is gamma is equal to gamma 1. So now again there is a delay in the turn off circuit. So it will give the such voltage, smaller voltage, and this is the gamma is equal to gamma 3, isn't it? So we found that we can obtain the variable voltage across the capacitor, and this is our objective, to obtain the variable voltage across the capacitor. Now, what is the voltage across capacitor? Voltage across capacitor VC is equal to 1 upon C integration gamma up to the omega t I dt. And finally we get, because what is I is here maximum at this point. This we are looking from this position. So I is equal to, we can write I cos of omega t. So by putting this value, we can get I upon omega c into bracket sine omega t minus sine gamma. This is the voltage across capacitor, isn't it? So it is just similar to the thyristor control reactor, where we have seen IL with the function of turn on delay angle, which is equal to V upon omega c into bracket sine omega t minus sine of alpha. This is for TCR, thyristor control reactor, just for the understanding purpose. And from, as again, therefore we can write as VC. This is for the thyristor control, and it is a GCSC, isn't it? So it is not only just for the reference. Okay. So we can write as a VC with the function of gamma, which is can be written as I upon omega c into bracket 1 minus twice gamma upon pi minus 1 upon pi into sine twice gamma. And we are writing this equation because we know that the IL alpha is equal to V upon omega. This is omega L, okay, omega L into bracket 1 minus twice alpha upon pi minus 1 upon pi into sine of twice alpha, isn't it? So this is somewhat analogy, okay, analogy with the TCR, and this is the equation for GC, isn't it? So from this one may write as one may draw the relation of angle gamma and voltage across capacitor. This is the objective, to analog with the help of this one. Okay. So say this is the degree, this is the, say, gamma, and this is 0. This is voltage VC is equal to VC maximum, voltage across capacitor, or you can write as a PU. It is in percentage PU over this value. Yes. So as the gamma increases, the first part it is decreasing up to the 90 degree. So this is pi by 2. Okay, just before this one, we have to understand. So what is the controlling region or range of angle gamma? So let it is a pi by 2, and we can delay the turn of delay angle up to the pi. Means actual range is from pi by 2 to pi. But we will consider this is equal to 0, and therefore it is pi by 2. So the range of gamma is equal to 0 to pi by 2 or 90 degree. So this is pi by 2, and it indicate this is the relation is 1 minus twice gamma upon pi. So this relation shows this one. Whereas the next part, 1 minus 1 upon pi into sine of twice gamma, this is give such type of curve. This is this relations or this one. And therefore, finally, we get the addition of these two. One is the voltage across capacitor. This is the total voltage VC. So when the delta gamma is equal to 0, the voltage across capacitor is maximum, or its rated value. As the gamma is increasing in this direction, and say 10 degree, it may be 20 degree, 30 degree, 45 degree, and so on. The voltage across capacitor decreasing. See here gamma is equal to 0, gamma is equal to say 10 degree. Here gamma is equal to say 30 degree, and so on. And again, if we increase this one, gamma is equal to say 40 degree, so voltage is go on decreasing. So by this way, this says the relation of gamma versus voltage across capacitor. Now finally, we'll get some VI characteristic of GCSC. That is very important. So it will work on two mode. One is the voltage compensation mode. Voltage compensation mode. Okay. So in voltage compensation mode, the value of capacitor, and this is the GCSC. Okay. This is two GTUs are there. This is VC. This is the current I, and this is JTUs are there. Okay. So it is the value of XC, or the value of XC is such a chosen that the voltage across VC, the VC should be maximum at when the current is minimum and XC. So at this one, and at the same time, the JTUs are conducted in such a way that even the current become maximum into XC, definitely the voltage across capacitor VC is going to increase. But part of the current is get conducted from the JTOs. Part of the current is going to conduct from the JTOs in such a way that the voltage across capacitor will remain constant. So that is called as a voltage compensation. So we will draw this VI characteristic of voltage compensation mode. Say this is the current I, and this is the voltage across capacitor. Voltage across capacitor VC. So say this is the minimum current, and say this is the maximum current. So even minimum current, the voltage across capacitor is maximum. Voltage across capacitor is maximum, And even after the voltage across, when the current increases, so part of the current is diverted from the JTO and rest of the current is going to flow from the capacitor XC in such a way that the voltage across capacitor will remain same. So this is called as a VC maximum here, and this is minimum value of the current, and this is the maximum value of the current. So this is the working area, of the or VI characteristic. Now we can draw the losses, percentage loss versus current. Same, this is the current I and this is the percentage loss, isn't it? So this is the value of minimum current, I minimum, and this is the value of I maximum. So under such condition, when the voltage across capacitor is 0, again, this is very interesting. This is VC is equal to 0. When the VC is equal to 0, when the current is going to divert from the closed switch. Say this switch is closed. So when the switch is closed, total current is going to divert from here, and the voltage across capacitor will be 0. And as the current going to flow from the JTO, it increases the losses. So up to this one, it increases the losses. And it indicate VC is VC with the function of gamma is equal to 0. But so up to this minimum value, the losses is minimum, but as it is gone increasing. Now second case, say this is the XC and current is going to increase. So it will deliver only the minimum current. Means at this point, the current will be minimum, isn't it? And rest of the current is going to divert from the partial conducting. That is that with help of turn off delay circuit, the current is going to divert it from here. So what will happen? The losses will be very small up to the minimum value of current, and after that, partial current is going to divert from the JTO, and rest of the current is going to flow from the capacitor. The losses will be smaller. So up to the minimum value, the losses is very small, and after that minimum value of current, some losses is going to increase. So it will indicate the losses versus current, percentage loss in the current. So here VC gamma is the voltage, isn't it? It's the VC is the where VC is equal to 0, or just we'll write as VC is equal to 0. This is the voltage compensation. And second part is the impedance compensation. Impedance compensation mode. So in impedance compensation mode, it is just similar to the ECR. This is the current, and this is the V maximum. Say minimum value of current, maximum value of current, and here this is the maximum voltage. So this is the control area. This is the control area. This is the I maximum. This is I maximum over this one. And what is the losses? The losses is higher because it is a so losses are higher when VC is equal to 0. When VC is equal to 0 is higher, and when up to the minimum value of current. So this is the losses. This is the current I, and this is percentage. So this is the JTO. In the next lecture, we will see thyristor switch series capacitor and thyristor control series capacitor. Thank you.